Okay, what's up, everybody? Welcome back to another fun day of proof, set theory, and logic. Today we're going to talk about the completeness of the reals. So completeness is a property you maybe have not encountered before yet. It is one that is often, in my opinion, presented in a needlessly confusing way. Maybe we will do a little bit of that. Hard to say. So there's a way of presenting it that makes like a lot of sense and makes it super clean to say. I will not start by saying that. Instead, I'll start by addressing it in like a more classic way, maybe slightly different than like how it is occasionally presented in different places, but hopefully still intelligible, and then give you like a more sensible way of looking at it, in my opinion. So we're going to start with section 6.3. The completeness of the reals. Okay, so here's the story. Here's the idea of it. Now, I'll try to illustrate this with an example here. Let A be the set of rational numbers such that Q is greater than 0 and Q squared is less than or equal to 2. And let's let B be the set of real numbers such that R is greater than 0 and R squared is less than or equal to 2. This marker is worse than I thought. Let's see. This marker better? Okay. Maybe. No, not very much. I bring good markers, then they get taken. Maybe this will work. We know that square root of 2 is not a rational number. So it is not in this first set, right? Okay. However, it is in B, right? It is a real number. Okay. Now, here's something to think about. Is there a biggest number in A? Is there? Is there a biggest rational number in there? There isn't, right? So, for instance, consider any, let's call it Q0 in A. Since square root of 2 is not in A, square root of 2 minus Q0 is greater than 0, right? Do you agree with that? Since after all you have to do is move Q0 over here, and that's what this part says, yeah? Okay, cool. So this is bigger than 0, yeah? All right. Take a decimal approximation of square root of 2 minus Q0, yeah? This is a rational number, right? After all, if you take like, I don't know what the number would be, like 0.1357, something like this, any decimal number you can write as a rational number just by moving over the decimal places and dividing, right? Do you agree with this or no? That is, you could write this as 1357, that number, which is an integer, divided by what? Well, I'd have to move the decimal. It would be a 1, 2, 3, 4 places. So 1, 10,000, right? Yeah, there we go. Okay, so that's a rational number, right? Okay. This is rational, yeah? multiply the denominator by 10. Still rational. Add this to Q0 to get a new rational Q1 such that Q0 is less than Q1, and that's still less than square root 2. You can repeat this as much as you want, right? Oh, you never run out of rational numbers. Just continually bigger and bigger and bigger and bigger. Never equal to square root of 2. All of them in A. Do you buy that? Does that process make sense, right? Like, you take square root of 2 minus Q naught. That's going to be some like crazy not terminating decimal, yeah? Just, cut off the rest of the digits after some point. Okay, there's a number, divided by 10 or something, right? Bigger, or a smaller rational number, bigger denominator, yeah? Add that to Q0. Okay, cool. There's a bigger rational number, still smaller than square root of 2. You can just keep doing this forever and ever. No big deal at all. What the heck? Okay. So, in some sense, A is, I'll say, not as filled in. As B. That is, you have like a sequence of stuff that gets really, really close to square root of 2, but you never actually get square root of 2, right? You're like missing a part. Okay. In fact, with Q itself, you can do this with any irrational number, can't you? Yeah? That is, the picture you kind of want to visualize is like, here's like the real numbers. And then anywhere you have something that is irrational, what you have is you have like a, if you have like a rational here, you in fact have infinitely many rationals in between the two. Between any rational and irrational number, there's infinitely many rational ones, right? But you still don't have that irrational number. Now, think about this. Pick any two rational numbers. Is there an irrational number between them? Totally. Here's an easy way to do it. Here's a super easy way to do it. Pick any two rational numbers, say like A and B, right? Okay, grab an irrational number and divide it by some power of 10 until what you get is smaller than that gap. Add it to A. It's an irrational number. Why? Well, if A plus an irrational number, let's call it B, I don't know, right? B over, I don't know, 10 to the n was rational. Well, if this was equal to some m over n, then notice all you have to do, remember this rational number here, I could write, let's say it, like I write it as like p over q, yeah? All you have to do is move that over, then you get b over 10 to the n is equal to m over n minus b over q, multiply it by 10 to the n, and suddenly you get that b is rational, right? Do you agree with that? Okay, so not only between like any rational and irrational number are there infinitely many rationals that get arbitrarily close to that irrational number, but between any two rational numbers, there's an irrational number. So they're like nicely like interlaced like this. But the reals, they have everything in there, right? So it's just like this nice continuous line. Well, the rationals, they have like so many holes. Between every two rational numbers, there is an irrational number. So that's something that's not in the rationals, right? And then between any rational and that irrational you can put in between, there are infinitely many rationals, meaning that there are, yet again, infinitely many more irrationals between those pairs of rationals. Oh man, the rationals have a ton of holes, right? They are like TV static, right? You know, like there's a thing, there's not a thing, not a thing, right? You know, it's just like it's a mess. Okay, so the rationals have just a ludicrous number of holes. Q has a ton of holes. A has just as many holes. B has no holes at all. What the heck is this? Why? Why is this so nice? Well, to talk about this in a meaningful way, we'll have to describe what the heck is going on. No, that's not a very good marker. Much better. What the heck is going on with A and B here? That is, how can we describe this missing upper piece? Since after all, anytime you have a hole, you can think about, like if you have like a missing piece right there, hey, you can just look at the rationals like less than that thing, and you just talk about there being this missing upper part, right? So understanding missing upper parts is kind of enough to understand the holes, if that makes sense. So how can we understand what's going on here? Let's get a couple of definitions to make it more clear. All right, so first up, a quick definition. You have perhaps seen this before, though perhaps you have not. Okay. Let A be a non-empty set of real numbers. We say a number, little u, is an upper bound for A if x is less than or equal to u for all x in A. That is, anything that's bigger than everything in that set would be an upper bound. A set of numbers does not necessarily need to have an upper bound. Consider the set of all real numbers. There's no upper bound, right? Okay. So you don't necessarily have to have one. Likewise, we say a number L is a lower bound of A if L is less than or equal, or sorry, X is less than or, L is less than or equal to X for all X in A. We say A is bounded above if A has an upper bound and bounded below if A has a lower bound. We also will sometimes say that A is bounded if it has both an upper and lower bound. Okay, so I think when you first see this, it seems really obvious and easy, right? Oh, it's a number that's bigger than the other numbers. But I think when you first actually start trying to put two and two together, it can get kind of weird. So here, let's do an example to make sure everyone's got it. All right. Let's let A be the set of real numbers such that A squared is less than 5. And let's let B be the set of numbers, say, 0 up to 7, not including 7, Well, even let's do some more. A, B, C, let's let C be the naturals, and let's let D be the integers. Yeah? Then, five is an upper bound for A. Would you agree with that? Maybe? Is 5 a number that's bigger than everything in there? 5 squared certainly isn't an A. 5 isn't an A because 5 squared is certainly bigger than 5, right? So 5 is certainly bigger than everything in A, right? Okay, cool. That's an upper bound. Exactly. Someone says, what about square root of 5? Totally also an upper bound. Yeah? Okay, yeah, very true, very true. May have multiple upper bounds. In fact, maybe we'll want to come up with some sort of a terminology to talk about, I don't know, like the smallest upper bound, like the least upper bound, yeah? Totally. Likewise, let's say, how about -3 is a lower bound for B. C has a lower bound has, instead of saying has a lower bound, has as a lower bound. What's a lower bound for C? 0.9, yeah, okay, sure. And no upper bound, while D has neither an upper bound nor a lower bound. Okay, so no upper bound, no lower bound, reasonable. There are also better upper bounds than the ones we gave for A. There are also better lower bounds than the ones we gave for B, right? Oh, well, maybe we should come up with some sort of a mechanism to talk about this fact. Maybe we should like describe a thing that lets us pick out from a whole host of potential lower bounds, one that is nice. This is the idea of a greatest lower bound and a least upper bound. So the definition, not so bad, says the following. Let A be a non-empty subset of the reals. We say a number U is a least, or is, I'll say a least right now instead of the, just for the moment, a least upper bound of A if U is an upper bound of A and for every other upper bound B of A, U is less than or equal to B. So if it's an upper bound and all the other upper bounds are bigger, yeah, the least one, reasonable. Okay. Likewise, we say L is a greatest lower bound of A if it is a lower bound and for every other lower bound of A, well, I should give a, let's say B of A, B is less than or equal to L. Okay, so greatest upper, or at least upper, greatest lower. You kind of flip it, right? Lower, you're thinking like less than, so you want the biggest one that's less than it. Least upper, upper meaning greater than, the least one that's greater than it. Cool. It's just like you're tightening on either side. Okay, cool. We also call the least upper bound of A the supremum of A, and the greatest lower bound the infimum of A. So just some terminology. Least upper bound, greatest lower bound, perfectly fine words to use for it. Sometimes a little bit longer to write, so people like to say infimum or supremum. Sounds cooler, I guess, right? Also, you can write inf and sup to abbreviate them, which is maybe a little bit nicer than GLB and LUB. Yeah, least upper bound, right? Lub and GLB looks weirder than infant sup, I guess, to some people. Okay. Long, lengthy definition, but do you feel like it makes sense? Hopefully so. Some of these ones can start to feel like a little bit much when you first encounter them, so that's entirely reasonable and to be expected. So let's just jump back over. What on earth? There we go. Okay, so there maybe is like a kind of obvious first thing you would want to show. Not so bad of a fact, but the way we're talking about greatest upper bounds, or least upper bounds and greatest lower bounds, infimums and supremums, seems to suggest at least that they are unique. That is, that you don't have two distinct greatest upper bounds, which perhaps is not such a weird thing to say. After all, via the trichotomy law, we do know that every pair of real numbers either has one bigger than the other or they're equal, right? So it seems like that would be a reasonable thing to say. So this is the first theorem regarding these. A quick fact, let A be a non-empty subset of the reals if U and V are least upper bounds for A, then U is equal to V. Yeah? Seems reasonable. How would you go about proving this? We don't actually have to do it right now, but just what's like a general kind of sketch you would do? Yeah, basically you would appeal to the definition of a least upper bound. You say, hey, look, from the definition, this means that both U is less than or equal to V, since U is a least upper bound. Since that happens, then also V is less than or equal to U. A, by trichotomy, you certainly can't have both of these unless U is equal to V, right? So that's basically where it comes out of. Hey, cool. Okay, I won't prove that right now. Perhaps maybe you'll prove something like that on a homework assignment or an exam. Who knows? But a good thing to consider. This means effectively that we can talk about least upper bounds in a meaningful way just in terms of the set. That is, if the set has a least upper bound, it is uniquely determined. And so you can just write something like sup A, or least upper bound A, to denote it, right? And there's no ambiguity about what number you mean. So that's kind of nice. Okay. Now, we have a similar fact for greatest lower bounds. But this is, so I mean, maybe I will write, should I write the whole thing? There is the exact same fact about greatest lower bounds. I will perhaps not write the whole thing now since it's basically exactly the same. So if instead of you just replace least upper bounds, you say greatest lower, then you get the same thing. Yeah? Cool. Okay, fine, good. 2 facts we won't prove. You can see how the proof would work, right? And instead, what we'll say next is that if a set has a greatest upper bound, then you have to have basically the same thing we saw happen in the first example occur. That is, the things in the set have to actually get close to that upper bound. So what does that mean? Well, I'll say it like this. Let A be a non-empty subset of R, and let U be the upper, or I'll say the least upper bound of A. If X is any number that is less than U, then there exists A in A such that X is less than A. What does this mean? Here's the way to think of it. You got the big old real line right here. You got some little chunk of it. Let's call it A. I'm going to draw this like an interval, but it doesn't need to be or something. It could be whatever. It could be crazy. It could have like a zillion holes in it, just like we've seen before. Okay. Now, what's the greatest lower bound of A? Well, it's going to be that top point, right? Whether that's actually in A or not is effectively immaterial, because what we're saying is that, hey, pick any point that's less than this. It could be anywhere to the left of this, anywhere you want. It could be like right here, X. What this is saying is that there is some point A between X and the greatest upper bound. It doesn't explicitly say that it's between it, but notice that if U is an upper bound, then U is bigger than everything in A. So certainly A goes between X and U. But notice you could pick any A and A and then just apply this again, right? It means that there's actually between the greatest upper bound and any element of A, an infinite number of elements in A that get closer and closer to it. Yeah? Kind of nice, yes. Okay, actually that's maybe like the kind of caveat to it, is that it is possible, I shouldn't say that there's an infinite number of elements. That is actually not entirely correct. If the greatest upper bound is, well, so maybe there's a piece here that we should be careful with. So for instance, take a 1-element set. What does this say then? What if, say, A is just the set 15? That's a non-empty subset of the reals. What's the supremum of A, the least upper bound? 15. Yeah? Okay, so pick any number less than 15. What's the number in A that exceeds that? It's 15. So I guess what I should say is that anytime you don't actually have the upper bound in your set, or the least upper bound in your set, the supremum, then you have this like infinite sequence getting close to it. So anytime we encounter a situation that was like our first example, then we basically have it work out exactly the same. Okay, cool. What I guess I'm trying to get at here is another way of looking at completeness, which effectively is about the convergence of sequences. So I will not phrase it in that way, but basically, think of it like this. What was going on with the rationals? With our example with the square root of 5 right at the beginning. You have things getting arbitrarily close to the square root of 5, rational numbers, but you never quite get there, right? That is, it's got a hole because you've got sequences that converge to things that are not rational. Does that make sense? Think about taking a decimal approximation of square root of 2. The more digits you add, the closer you get. Yeah? And you can imagine that as the number of digits goes to infinity, you get arbitrarily close to approximating square root of 2, right? Well, all of those decimal approximations are rational numbers. And so you've got a sequence of rational numbers converging to something that is not rational. what completeness is as a property, this idea of like lacking these holes, basically says that your convergent sequences converge to an element of your set. That is, that the limits of sequences are not things outside of your set. So if you have stuff in your set that gets close to something, well, that thing that it gets close to belongs to your set. This is not true for the rationals. That is, if you think about what we've talked about so far, we've talked about the algebraic properties of R, that is, R is a field, right? We've talked about some of the order theoretic properties of R and how they interact with the algebraic properties, that is, R is an ordered field. But think about the rationals. The rationals are also an ordered field. It's a field, got the same algebraic properties as the reals. It's ordered, the same ordering even, right? Oh man, what the heck distinguishes the reals from the rationals? They're different, but what is it? It must not be the algebraic properties straight up like that, like from the field business. I mean, there is a way of seeing it in terms of algebraic properties. And it must not just be directly, it being an ordered field. There must be some sort of additional thing, some additional special piece. And it's this completeness property that does distinguish the two. So having limits of sequences converge to be actually things in the set. That is, if you take a convergent sequence of real numbers, does it ever converge to something that is not a real number? No, right? Anytime the sequence converges, it converges to a real number. This is not true for the rationals. You can have a convergent sequence of rationals, like they get arbitrarily close to something, but that something is not a rational number. It is a real number. Oh, okay. Kind of wild. Okay. So there's one way of looking at it. Fair enough. Now, let's see if we can prove this. Okay. What would you do to start to prove this? How would you get there? Well, we've got a least upper bound. We've got something that's less than u. Okay. So for the proof, which is actually fairly short, let's let u be, I'll even just leave it as a, or I'll say, even though we know it is now distinct, let u be a least upper bound for a, and suppose x is less than u. We will go by contradiction, effectively. So assume there is no a in a such that a is greater than x. Then a is less than or equal to x for every a in a, and x is an upper bound of a. But x is less than u, and u is the least upper bound of a, i.e., u is less than or equal to x. So we have both u is less than or equal to x and x is less than u, a contradiction. Hence, there must exist a and a such that x is less than a. Otherwise, x would be an upper bound that is smaller than the least upper bound, meaning that it would not actually be the least upper bound. That would be a contradiction, right? Oh, okay. So we always get this property. At any time the least upper bound does not actually belong to the subset, then we've got this bit of a mess here where we have like infinitely many things there, yeah? Crazy. Okay. So the reals have kind of a lot of holes. Here are some ways to describe when we don't have holes. So these we'll call the completeness axioms. So like the completeness properties of the reals, I guess, is what we'll think of this as. Like what distinguishes the reals from other fields? What distinguishes it from Q? It's not purely the field property, not purely the ordered field property. It's the complete ordered field property here. So let's go. All right. I'll even just, sorry, I said axioms. Let A be a non-empty subset of R if A has an upper bound, it has a least upper bound. Likewise, if it has a lower bound, it has a greatest lower bound. Okay, what does this mean? How does this tie back into everything else? Remember, we were saying, hey, we can figure out how to talk about holes basically entirely by talking about when you lack upper bounds, since you can always just look at the holes effectively from one side, right? How we talked about at the beginning, like, hey, can you get close to it? You know, you could think about the same thing on the other side, and then we get, you know, analogous statements for greatest lower bounds and so on. But think about the rationals. Now, if we go back to the set from before, where we had A was Q a rational such that, I'll write it this way, 0 is less than Q, that is Q is a positive rational, and Q squared is less than 5. I was even say less than or equal to. How about? Or 2, not 5. I think we did 2, because we proved that square root of 2 is irrational, right? Okay, upper bounds for this. There are many rational numbers that are larger than square root of 5. Is there any smallest rational number that is bigger than square root of 5? No. Yeah, and for exactly the same reason as before. We can just go, hey, look, here's square root of 5. Suppose you've got a rational number p over q right here. Yeah? Take p over q minus square root of 5 and do a decimal approximation up to some number of decimal places, right? Cut off some of the remaining decimal places. Well, this is a number that is smaller than that difference, since you're just cutting off decimal places. And you could add it to square root of 5 to get a new rational number in between them, right? Maybe? You know what I'm saying? Yeah? Okay, so you can always find another rational number and then just repeat the process, and you can get another one and another one and another one. And arbitrarily close, all of them rational numbers. Uh-oh. Basically what you're doing is you're going like, hey, let's take like a decimal approximation to square root of, not 5, 2. I keep doing 5. I don't remember why I'm doing 5 so much. But basically, you're looking at a decimal approximation of square root of 2 that is too big, and you slowly make it closer and closer. Yeah? Fair enough? Okay. So it's easier to see the too small decimal approximation because it's just like the decimal approximation, just keep adding more digits. While one that's a little bit too big kind of seems weird at first. But basically, it's just doing the same thing on the other side, right? And hey, you can get arbitrarily close to square root of 2 with rational numbers. There is no least rational number that is larger than square root of 2. There are arbitrarily many rational numbers, infinitely many of them, that are bigger than square root of 2. Okay, so describing holes can be accomplished effectively just by talking about when you have least upper bounds and greatest lower bounds. That is, if you have an upper bound, do you always have a least upper bound? For the rationals, you have plenty of upper bounds for square root of 2, but you don't have a least upper bound. Okay, So there's a hole. Does that make sense? All right. Hopefully it does. If it doesn't, that's all right. But we get a lot of nice things out of this. Just let me jump cameras and do a quick little bit of erasing here. The next one that is very nice is the Archimedean property. So, oh man. Come on, spray bottle. And we can talk about that momentarily. Let's see. So what a lot of this is building to, what we're going to kind of get to next is, I guess I kind of want to spoil the fun a little bit. Maybe not spoil the fun, hopefully not, but give like a bit more sense of why we're doing some of this. Like why do we care about all these holes? Here's a way to think about it. What we're going to show you is that there are genuinely more real numbers than there are rational numbers. That there are genuinely more real numbers than there are integers or natural numbers. And one of like the easiest ways to see that this is kind of probably going to be the case, I think, or to get some intuition for why this is like not by itself like a weird thing, is to see just how much how many things the rational numbers lack. That is, between any two rational numbers, there is an irrational number, right? We talked about how to get to that, yeah? And between any rational and irrational number, there are infinitely many rationals, meaning that there are infinitely many more irrational numbers between any pair of rationals, right? Like they have so many holes. They are missing so many parts. They are missing so many things that perhaps won't seem as weird when we show you that there are genuinely fewer of them. Which maybe seems like not a weird statement to say like, okay, yeah, sure, there's more real numbers, but like think about this. This is actually crazy and was like a revolutionary idea when it was first introduced. This means that there are different sizes of infinite sets. That there's not just like one infinity, but actually like different sized infinities, which is weird, right? That's crazy. We're going to build to that. We're going to get to that. I'm going to show you that that's true. But hopefully this serves as some good motivation for why you should accept that that is the case. I mean, we'll prove it, right? But why it is not maybe the craziest thing to think of. Okay, so here's a nice little theorem. So this is the Archimedean property. Okay, if x is a real number, then there is a number, I'll say nx, in the natural numbers, such that x is less than or equal to nx. That is, every real number is less than or equal to some integer. Can you imagine this? Round up, right? Okay, fine. Perhaps not that crazy of a thing when you first see it, but by itself, the statement that perhaps does not seem too strange is actually kind of interesting, right? It says the same thing as with the rationals, that you always have like a bigger rational. But even with the integers, it's the case. Okay, let's do a quick proof. We will use this at various points. So if it seems like it's like an overly simple thing, it is an important tool in our arsenal. But let's see if we can prove this. What would you do? Contradiction. Okay, let's see. Yeah, all right, so by way of contradiction, assume not. I'll even make clear, I'll say i.e. assume there is a real number x such that, st, such that n is less than x for all n in the naturals. Then x is an upper bound for n. Applying the completeness axiom. And perhaps I use the term completeness axiom here because your textbook uses it. It is not just like a thing that we're just assuming for free. This is actually a fact we can prove. You could impose this as an axiom, like something you're taking for granted, but you don't have to actually here. There's no reason to do something like that and add extra assumptions needlessly when they're implied by previous things. That is, you can actually show that the completeness axiom, you can just state it as like a theorem and show that this is true. But for now, we're just going to keep the same, we're going to proceed in the same manner as the textbook and leave that alone for the moment, though I want to mention it since I don't want to lead you astray. But applying the completeness axiom to n, since it is a subset of R, there is a least upper bound. This tells us that there is a least upper bound to n, i.e. a number m in the reals such that n is less than or equal to m for all n in the naturals, and such that m is less than or equal to, I'll say, oh, what letter should I use? I'll say B for all other upper bounds B of the naturals. Yeah? Okay. Now, since m minus 1 is less than m, this tells us that there is a natural number n such that m minus 1 is less than n, right? That is, as we proved in the theorem over there, let's jump back to it, hopefully that's not my camera. If x is anything less than the least upper bound, then there is some a in your set that is bigger than that x, yeah? Hence, m minus 1 is less than m, the least upper bound, so there is some natural number n such that m minus 1 is less than n. But this says m is less than n plus 1, which notice is in the naturals, so m is not an upper bound. This is a contradiction. Do you agree with that? That is, we assumed that m was an upper bound. That is, it's a number such that n is less than or equal to m for all n in the naturals. And we said, hey, look, well, m minus 1 is smaller than m. So, as we've shown, there must be a natural number bigger than that. Fair enough. Okay. But then adding, we just get that m is less than n plus 1, which notice is a natural number itself, so m is less than a natural number. That is, it doesn't satisfy this property up here, which an upper bound must satisfy. Oh, a contradiction. So the result must be true. Okay, kind of cool. Kind of nice. Archimedean property proved. And looking at the clock, we are done for the day. All right. Actually, wait, do we go till 5 after? No, we go to the top of the hour. Okay, cool, right on. See you guys later. Sorry for keeping you 2 minutes late. We'll have more fun.
That was a question.